Hello everyone. In this lecture we will discuss wave diffraction and reciprocal lattice. X-ray diffraction is a technique used to study crystal structure because it's non-destructive technique. Comparing to other techniques, it's like kind of a cheap technique. We should know that diffraction depends on crystal structure and wavelength. So two things we have to consider here while studying X-ray diffraction is the crystal structure and the wavelength. Assuming that we have a wave scattered by a single atom at a lattice point R. Now the scattered wave is detected at a point R that is far from that atom. However, at large distances, the spherical wave fronts of the scattered wave are almost planar, with a wave vector k prime directed from R to R prime. Now, considering that the wave frequency is not changed while scattering, so the wavelength will also be the same in such a way k prime equal to k. Now k prime is the scattered wave vector and k here is the incident. Now we have to consider that the scattered wave can be built up from two factors. The first one is e to I k dot r and the phase of the incident wave at that atom. We also have to consider the phase change k prime minus r minus capital R in propagating from R capital to R. In this case here, the wave vector of the scattered wave equal to a e to I k dot r multiplied by the phase change e to I k prime r minus capital R. Or in other words, a e to I k prime dot r multiplied by e to I minus I k prime minus k r. We just here rearrange the product of exponentials in this one here. The coefficient a in this case, which has to be much less than 1, is just to remind you that small part of the incident radiation is scattered by that atom. Now to generalize for all atoms, we have to sum all individual waves over all atoms of the crystal, and in this case psi scattered here, or the wave vector here, total R equal to a e to I k prime dot r times summation over all atoms e to minus I and the phase difference here dot r. Now the phase factor here expresses the fact that the scattered wave has a wave vector k prime, this one here, and the second one, this part here, depends crucially on the particular lattice, determines whether waves will be scattered strongly in the direction k prime. Now just to mention that the scattered wave is large only when all of the terms in this one here have the same phase. Now let's start with the second factor, e to minus I k prime minus k dot r1 equal to e to minus I k minus k K prime here dot R2, or e to I K prime minus K dot R1 minus R2. This has to be equal to 1, and remember R1 minus R2 is just lattice vector. Therefore, the condition for constructive interference becomes e to I K prime minus K dot R equal to 1. And remember, this is the condition for constructive interference. Here, the condition. It's very important here to remember that the solution of this equation will lead us to a concept of reciprocal lattice. Now let's start here with reciprocal lattice. In order to find the solution for this equation here, e to I K prime minus K dot R equal to 1, we have to define the difference K prime minus K as G in such a way e to I G dot R equal to 1, or in this case G dot R equal to 2 pi N. N in this case is integer. It could be positive, negative, or even 0. And R in this case here is any lattice vector. Now this condition here must be satisfied for a set of primitive lattice vectors in such a way G dot A1 equal to 2 pi N1 and G dot A2 equal to 2 pi N2 and G dot A3 equal to 2 pi N3. And again N1, N2 and N3 all are integers. Therefore, the solution G here is equal to 2 pi times N1 over A1 x hat plus N2 y hat over A2 plus N3 over A3 z hat. From this, we can define B1 here equal to 2 pi over A1, and B2 here it's 2 pi over A2, and B3 equal to 2 pi over A3. In this case here, remember that A1, A2 and A3 are lattice vectors in real space, but B1, B2, B3 are the primitive vectors in reciprocal space. And remember here, A1, A2, A3 has a dimensionality of length, but B1, B2, B3 has a dimensionality of reciprocal of length. So A1, A2, A3 are primitive vectors of the direct lattice, sometimes called real space, and G will be N1, B1, N2, B2, N3, B3 in such a way B1, B2, B3 are primitive vectors in the reciprocal lattice. So primitive in reciprocal lattice. These primitive vectors are given as B1 equal to 2 pi A2 cross A3 as vectors here, divided by A1 dot A2 cross A3, and B2 is defined as 2 pi A3 cross A1 and divided by A1 A2 cross A3, and B3 is defined as 2 pi A1 cross A2 divided by A1 dot A2 cross A3. And pay attention here, it's cyclic. B1, A2, A3, B2, 3, 1, and B3, 1, 2 divided by the primitive volume. Now, as soon as we define the primitive vectors A1, A2, A3, these vectors of the direct lattice are usually specified simply by giving coefficients of AI in square brackets. In general, R is defined as U1 A1 plus U2 A2 plus U3 A3, or its equivalent to, in square brackets, U1 U2 U3 here, and G generally is defined as V1 B1 V2 B2 plus V3 B3, or equivalent to V1 V2 and V3. It's good to mention that crystallographers prefer to omit the commas. For example, they prefer to use this notation, for instance, 1, 3, 2, and this notation means, as we mentioned before in Miller indices, is 1, 3, minus 2. Notice that there is a very close connection between reciprocal lattice vectors and lattice planes, as we discussed before in Miller indices. So let's imagine that a plane wave E2 I G dot R in a crystal. In this case here, this wave would have the same phase G dot R here equal to 0, the modulo in this case 2 pi. At every lattice point R equal to R. Now don't forget that every lattice plane is perpendicular to G, and therefore a wavefront of the wave is E2I G dot R. This means that the spacing of the lattice planes must be an integer multiple of wavelength lambda G. In this case here, lambda G equal to 2 pi over G, and therefore D here equal to n lambda G. In such a way, n cross and lambda G is equal to 2 pi over G, n equal to 1, 2, 3, etc. Now by writing G as NGS in this case here, in such a way, GS equal to L1, L2, L3 is the shortest reciprocal lattice vector in the direction of G, where G equal to V1, V2, V3. and n is the greatest common divisor of v1, v2, v3. Now n here is the greatest common divisor of v1, v2, v3. Therefore, d equal to 2 pi over gs, or simply 2 pi divided by L1 B1 L2 B2 L3 B3, and L1 L2 L3 are Miller indices that we discussed before, but for this one are Miller indices of the lattice planes which is perpendicular to G. As an alternative definition of Miller indices, let's take position vector R as R here equal to x1 A1 plus x2 A2 plus x3 A3, and GS here dot R is defined as or equal to 2 pi L1 x1 L2 x2 L3 x3, which in this case equal to 2 pi. If we set x2 equal to x3, which equal to 0, in this case here the plane will cross the x1 axis at x1 equal to 1 over L1. So set x2 equal to x3 equal to 0. In this case here the plane will crosses the x1 axis at x1 equal to 1 over L1. With the same technique, set x1 and x2 equal to 0. In this case x3 equal to 1 over L3, and x2 will be equal to 1 over L2 if we set x1 and x3 as 0. In other words, the Miller indices L1, L2, L3 of the lattice plane might be defined as the reciprocals of their intercepts of x1, x2, and x3. Let's define Bragg's law. As we mentioned before, k prime minus k is actually equal to g, and g in this case is the reciprocal lattice vectors. Now, Bragg used this result to find an alternative definition of the diffraction condition. So if this is a lattice plane, this one here, and this is the incident wave vector k, and this is the reflected one, this one here, it's found as k prime, and g, this is g, this one here, this is k prime, and this is g, and this is theta, it's named theta b. The length of k and k prime is equal to 2 pi over lambda. So the length of k and k prime equal to 2 pi over lambda, which means the incoming and outgoing wave vectors are inclined at equal angles to the plane normal to G. And this is actually called Bragg's reflection. And the angle between the plane and the wave vector of the incoming and outgoing waves is called Bragg angle, and it's actually denoted by theta b, this one here. And the angle between the forward directions of the two waves, the incident and the reflected or the incoming or outgoing waves, is equal to 2 theta b. And remember, only a few values of theta b can give rise of diffraction. As we mentioned before, not all the incident wave will be diffracted. Therefore, G here equal to 2k sine theta b, or equal to 4 pi over lambda sine theta b. And from d equal to n lambda g, or equal to n 2 pi over g, we will have g equal to 2 pi n over d, and remember n equal to 1, 2, 3, etc., where d is the spacing of lattice planes which is perpendicular to G. Now, by equating this equation here and this equation here, we will get n lambda equal to 2d sine theta b, and equal to 1, 2, and 3, etc. And this is actually Bragg's law. In other words, the path difference for two waves is multiple of n of the wavelength, and usually defined as the order of diffraction. Now let's define the Brillouin zone. In two-dimensional lattices, we define winner side cell in real space. In three-dimensional lattices, we will define what's so-called Brillouin zone. But Brillouin zone, it's actually winner side cell, but in reciprocal space. Now, to define the Brillouin zone, follow this procedure. First, almost the same as winner side cell, but in this case, a slight difference here. First, select a vector G from origin to reciprocal lattice point. Then construct a plane normal to the vector G at its midpoints. Now this plane forms a part of a zone boundaries. The X-ray beam in the crystal will be diffracted of its wave vector. And then the diffracted beam will then be in the direction of k minus j, with delta k equal to minus g. Let's write them down. So you pick up a central atom with its nearest neighbors like this, and remember it's in 3 dimension, it's not in 2 dimension. Now you take the midpoints with planes. It's not like winner side cell, it's take the midpoints with the planes. Now the volume here is called Brillouin zone. Now let's define the reciprocal lattice to simple cubic lattice. Now remember, The primitive translation vectors of simple cubic lattice is A1 equal to AX hat, A2 is equal to AY hat, and A3 equal to AZ hat. Now, the primitive vectors in reciprocal space B1, it's equal to 2 pi over A2 cross A3 divided by A1 dot A2 cross A3. You substitute these primitive vectors in real space with this one here, you will find B1 is equal to 2 pi over A x hat, and B2 same procedure equal to 2 pi over A y hat, and B3 equal to 2 pi over A z hat. And by deblocking here, you will find A1, A2, A3 is defined in terms of x hat, y hat, and z hat with some factor here. And B1, B2, B3 is defined as x hat, y hat, z hat. So the reciprocal lattice of simple cubic lattice is actually another simple cubic lattice with small difference is a lattice constant. In this case here, it's equal to 2 pi over A. This one here. In real space, it's A. Now, in reciprocal space, it's 2 pi over A. Now, if we have a group of atoms, one dimensions here, this is A here. Now, in reciprocal space, it's actually, this is B. Now, the Brillouin zone boundaries is from minus, okay, here, minus pi over A to pi over A. Now, if this is B, so this is the Brillouin zone boundaries, so minus pi over A to pi over A. This is the Brillouin zone boundaries. Or in other words, we can define plus or minus half B1 equal to plus or minus pi over A x hat, and plus or minus half B2 is defined as plus or minus pi over A y hat, and plus or minus half B3 equal to plus or minus pi over A z hat. Now let's find the reciprocal lattice to BCC lattice. In BCC, A1 it's equal to half A minus x hat plus y hat plus z hat, and A2 equal to half A x hat minus y hat plus z hat, and A3 is equal to half A x hat plus y hat minus z hat. And the volume of the primitive cell in BCC is A1 dot A2 cross A3 equal to half A cube. Now B1, we just substitute this back in the B1, B2, B3 equations. You will find 2 pi over A y hat plus z hat, and B2 equal to 2 pi over A x hat plus z hat, and B3 equal to 2 pi over A x hat plus y hat. Now if we deblocking to the results here, this one here and this one here, this is similar to the lattice primitive vectors for FCC in real space. So the reciprocal of the BCC structure is actually an FCC structure. And the shortest G's are the following 12 vectors, which are 2 pi over A plus or minus y hat plus or minus z hat, and 2 pi over A plus or minus x hat plus or minus z hat, and 2 pi over A plus or minus x hat and plus or minus y. And remember, these are the Brillouin zone boundaries. And remember, in FCC we have 12 nearest neighbors, and here we have 12 Brillouin zone boundaries. Now the volume of the primitive cell in reciprocal space for the BCC structure is actually same rule, but in this case we use B dot B2 cross B3, and you just substitute B1, B2, B3, you will get 2 times 2 pi over A cube. Now let's find the reciprocal lattice to FCC lattice. In FCC, A1 equal to half A y hat plus z hat, A2 equal to half A x hat plus z hat, and A3 equal to half A x hat plus y hat. And the volume of the primitive cell in real space V equal to A1 A2 cross A3, all vectors by the way, equal to A to the power 3 over 4. Now use these vectors, this one and this one, this one here, to find B1, which equal to 2 pi over A minus x hat plus y hat plus z hat, and B2 it's equal to 2 pi over A x hat minus y hat plus z hat, and B3 equal to 2 pi over A x hat y hat minus z hat. And from the definition of B1, B2, B3, we can tell that these vectors are similar to BCC structure. So the reciprocal of FCC structure is actually BCC structure. And again, from these definitions, we can find the shortest G's, which is 8 possible vectors plus x plus y minus z, this is 1, and minus x minus y plus z, this is the second one, minus x plus y minus z, this is the third one, minus x plus y plus z, minus x minus y minus z plus x plus y plus z plus x minus y plus z and plus x minus y minus z. Or in other words, you just write them plus plus minus 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 plus minus plus minus minus plus plus minus 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 plus 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 minus plus plus minus minus. Now if you count them, we'll find that there are 8 shortest G, which is actually first nearest neighbors for BCC structure. Now in this case here, the Brillouin zone boundaries is actually 2 pi over A times plus minus x hat plus minus y hat plus minus z hat. And from here possibilities come plus x hat plus y hat plus z hat, or plus x hat minus y hat minus z hat, and so on. In order to implement X-ray diffraction in studying the crystal structure, we should define structure factor. Now, if we have more than one atom per lattice point, the sum, as we discussed before, the total one here, just I write this down, e to I k prime dot r times summation over r e to minus I k prime minus k dot r can be generalized and become psi total r equal to a e to I k prime dot r times summation over r. Now, sum of all atoms starting from j equal to 1 to m fi e to minus I k prime minus k dot r plus r j. In such a way, the atoms associated with a particular lattice point r can be taken as r plus r j, this one here. And to simplify, this one here equal to total e to a e to I k prime dot r times summation over r e to minus I k prime minus k dot r times summation over all atoms fi e to minus I k prime minus k dot r j. And in such a way, the second factor, this one here, involving the sum over all lattice points r, and it's large only if k prime minus k is a reciprocal lattice vector. And the last term, this one here, involving the sum over all j, which needs to be considered only for those special values when k prime minus k equal to g. And therefore, Sg equal to sum of all j equal to 1 m fi e to minus I g dot r j. And Sg in this case is known as structure factor. And Fj is the atomic form factor, which defined as Fj equal to integration over atom j and j of r e to minus I g dot r d cube r, and j is the number density of electrons, number density of electrons in atom j, and the origin of coordinates for the integration is taken to be the center of the atom. From the above definition, atomic form factor decreases with increasing g, and therefore the diffraction tends to be strongest for small values of indices V1, V2, and V3. Now let's find the structure factor for the cesium chloride structure. As we remember that cesium chloride is a simple cubic crystal, although it looks like BCC, but it is simple cubic crystal. In this case, here the atomic positions for cesium and chloride is as this. So let's name cesium as atom A and chloride as atom B. Now the atomic position Ra for the cesium, it's equal to 0, 0, 0 and times lattice constant A, and the atomic position for the chloride, which is B in this case here, equal to half times the lattice constant A. Therefore, G in this case, it's equal to V1, V2, V3 times 2 pi over A, in such a way Vi are all integers. Therefore, the structure factor equal to the form factor for atom A e to minus I g dot Ra plus the form factor for atom B e to minus I g dot R B. In other words, Fa plus Fb exponential minus I 2 pi over A times V1, V2, V3 times half A. Remember, G equal to V1 B1 plus V2 B2 plus V3 B3, and R equal to U1 A1 plus U2 A2 plus U3 A3. In this case here, U1, U2, U3, it's equal to half. And remember the orthogonality condition, Bi dot Aj equal to 2 pi delta Ij, in such a way delta Ij equal to either 0 or 1 when I equal to j, and 0 when I is not equal to j. By using these definitions here, now the structure factor will become as this: Fa plus FB exponential, now this is dot product, this one here, this is dot product for R and G, exponential here minus I pi times V1, V2, V3. And keep in mind that E2 plus or minus I pi, it's minus 1. Therefore, the structure factor equal to FA plus minus 1 V1, V2, V3 times FB, and the answer will be FA plus FB if V1 plus V2 plus V3 is even, and FA minus FB if V1, V2, V3 is odd. Now, if V1, V2, V3 is even, this will be positive, so the answer will be FA plus FB. Now, if V1 plus V2 plus V3 is odd, in this case, the answer will be FA minus FB. This one here. Notice that the intensities of the diffracted waves are proportional to SG square. Therefore, it's expected to see diffraction spots with two different intensities in the ratios of FA plus FB square to FA minus FB square, which crucially depending on the values of V1, V2, V3. Now let's find the structure factor for BCC structure. Now in BCC structure, remember there's an atom in the middle of the cube and 8 atoms in the corners. So the total atoms used to build this structure are equal to 2. But the difference between this BCC and cesium chloride is BCC here, atom A is the same as atom B. Therefore, the atomic position, we just have RA. Here we have actually two positions, 0, 0, 0 and half, half, half. In this case here, if we substitute this back in the structure factor formula, Sg in this case, it's equal to same result as in the cesium chloride, but Fa is the same as Fb, so F here plus F equal to 2F in this one here, and F minus F here, which equal to 0. Now 2 pi if and only if V1 plus V2 plus V3 is even, and 0 if and only if V1 plus V2 plus V3 is odd. This means that there's no diffraction occur when V1, V2, V3 is odd. This means there's no diffraction when V1 plus V2 plus V3 is odd. For instance, 1, 1, 1, this one here, there is no diffraction from that plane. The reason for that is a destructive interference between the waves scattered by the atom at 0, 0, 0 and half, half, half. Or in other words, no diffraction profile will appear from the plane 1, 1, 1 for BCC structure, and again for 2, 2, 1, and like 1, 0, 0. And there is a diffraction profile for the planes 2, 1, 1, 2, 0, 0, 2, 1, 3. Now let's find out the structure factor for FCC structure. For monoatomic FCC structure, the atomic positions are A, in this case here, is 0, 0, 0, A, 0, half, half, A, half, 0, half, A, and half, half, 0, A. If we substitute this back in the structure factor formula, you will find that the structure factor equal to this one here, and only two integers is active here. The third one is 0, which means the structure factor equal to 1 plus minus 1 to the power V2 plus V3 plus minus 1 V3 plus V1 plus minus 1 V1 plus V2. In such a way, this factor here comes from R equal to 0 A1 plus half V2 plus half V3. When you dot product this one with G, with R, you will get E2 minus I pi over A times V2 plus V3. And same procedure for this one here, same procedure for this one here. In this case, times A and G dot R equal E2 minus I pi times V2 plus V3. Now same procedure for this one here and this one here. Remember, E2 minus I and pi, it's equal to minus 1 to the power n, and in this case it's V1 plus V2 or V2 plus V3 or V1 plus V3, this one here. From that we get this definition here. Now if V1, V2, V3 all even, let's see what's going to happen here. If V1, V2, V3 all even, in this case here, let's just apply for the structure factor, this one here, this one here. Now V2 plus V3, even plus even, it's even, minus 1 to the power even number is just 1. Now this one here is just 1, and this one here is just 1, same definition. In this case, in the structure factor, it's equal to F1 plus 1 plus 1 plus 1, or in other words, it's equal to 4F if V1, V2, V3 all even. Now if V1, V2, V3 all odd. In this case, let's see what's going to happen here. If V2 plus V3 odd plus odd is even, in this case, this one here equal to 1. Now, this one here, again, odd plus odd is even. Minus 1 to the power even number is 1, and minus 1 to the power even number is 1. In this case here, 1 plus 1 plus 1 plus 1, it's equal to 4f. Now, let's just add another condition here, or V1, V2, V3 all odd. Now let's see what will happen if we have mixed numbers like V1 and V2 even and odd. Now if we have mixed numbers, in this case here, let's see, if we have like, let's just pick up numbers 1 0 1 1 0 1. So in this case here, V1 it's equal to 1, V2 0, and V3 1. Now V2 plus V3, 0 plus 1, in this case this one here is odd. Minus 1 to the power odd number, it's minus 1. Now this one here, V3 plus V1, 1 plus 1, it's even, so this one is 1. Now V1 plus V2, it's odd, and this one minus 1. Therefore 1 minus 1 plus 1 minus 1, it's equal to 0. So if we have mixed numbers, then the structure factor is 0 if V1, V2, V3 are mixed numbers between even and odd. In summary, if we have, let's see, 2, 0, 2 plane, and you will see a diffraction profile for the plane 2, 0, 2, and you will see a diffraction profile 1, 1, 1, and you will see a diffraction profile for 3, 1, 1, but you will never see a diffraction profile for 2, 1, 0 or 1, 0, 1 or 3, 0, 1. So you will not see diffraction profiles for these planes, and you will see for these planes.